Okay, let's get started. Did you do this with Lorraine? Did you talk about states of matter in chemistry?
No. Yeah.
But you've mentioned the terms, have you? Solid, liquid, and gas. Okay. Right, so this is water, and this is what water would look like close up, but you would know this from chemistry. What are we actually looking at here? H2O molecules, aren't we? As you know from science, things are made of atoms, but more importantly, these atoms come together to form molecules. So actually, in chemistry, what do you say a molecule is? What's your definition of a molecule in chemistry?
Atoms of different elements chemically bonded.
No, atoms of, no, it doesn't have to be different elements. Atoms from one or more elements
Yeah,
that
yeah,
can
yeah.
be bound together.
Something like that, yeah. Sounds about right, doesn't it? You nearly have it. A molecule is an electrically neutral group of two or more atoms held together by chemical bonds. An example is water, which is H2O. Okay, I think you should write that down. It'll be good for both physics and chemistry. Okay, got that definition? When's your chemistry exam? Friday? Yeah. Maybe this definition will be in it. That would be good for you. Okay, you got that, Diego? Yep, yep. So, what does water look like at the molecular level when it is frozen solid as ice? Or what about when it's a liquid or even a gas? So here's a picture here of the three different states that water can be in. So firstly, this is what the H2O looks like when it's ice. This is when it's liquid water, and this is when it's steam. How would you describe the differences here? So what's different about this one?
Forming like a net.
Yep. Grid, lattice.
Yeah.
What else could you say? Stable, yeah. It's locked together. In the second picture, what you can't see is the molecules are moving around. But they're still close together. And the last picture?
They're super hard.
Yep. They're free, individually. Yeah. You know these words. When we go from solid to liquid, that's called melting. When we go from liquid to gas, that's called evaporation or boiling. Boil something. When we go from a gas to a liquid, that's called condensation. And when we go from a liquid to a solid, that's called freezing. And there is one for jumping the middle guy from going solid to steam. Sublimation, yeah. To move to the right, you have to add energy. What energy do you add? You add heat energy. And to move to the left, you remove energy. What removes energy? No, heat before adding energy. How do you go from steam to liquid to ice? How do you remove energy?
Releasing.
Huh? What do you do?
Releasing heat.
Yeah, but how? How do you release heat? I'll give you a clue. You have it at home. Keeps your Coca-Cola cold.
Freezing.
What do? You put it in the fridge, don't you?
Mm-hmm.
Yeah. A fridge is designed,
Capturing.
a freezer is designed to remove energy from the food. And by taking the energy out of the food, it brings the temperature and the energy down and makes it freeze. Right? You know this, don't you? It's called a heat pump because it's like you pump the heat out of the food. Right? Where does when the fridge takes the heat out of the food, where does it put it? Where does it go?
A special liquid.
No. Well, the liquid is how it takes the heat out, but where does this heat go? The fridge takes the heat out of the food, and where does it go? Yeah, it comes out the back of the fridge on the ground. If you put your hand down behind the fridge at the back, I think you'll feel the heat coming out. It's being taken out of the food. Yeah. I'm sure if you had cats at home, you would see them. Like, no, nobody has cats. No one has cats. Okay, then you don't know this. Right. I want you to draw this with the words. Make sure you get all those words. Don't want to draw the pictures?
I misdraw pictures.
Well, it'll help you remember.
Okay.
Because sometimes in the exam they ask you to describe the difference in the tree. Got it? Yeah? Yeah? Okay. Now, we have the definition of a solid. It's quite long. You don't need it all for the exam. In a solid, the position of the atoms are fixed. So if you look at the picture here, can you see how they're, I think, Harry, you said they're stable. Didn't you? Or who said they were stable? You said they were stable, yeah. So you mean like they don't move, they're fixed. This is due to the friction between the molecules. It's provided by metallic covalent or ionic bonds, which you know about in chemistry. Only solids can be pushed on by a force without changing the shape. So if you have a solid, you can push it, it doesn't change the shape. They are resistant to deformation. What's deformation?
Basically
Changing the shape, yeah. They tend to be strong enough to hold their own shape in a container, and they're usually denser than liquids. When a solid becomes a gas, that's called sublimation. Now, you don't need all this for the exam. I think it's enough to say the first two sentences. You don't need the third sentence because that's chemistry. We don't actually talk about these bonds in physics. And the rest is kind of obvious. So I recommend you write down the first two sentences. And also, you should make note of this word called sublimation, which a couple of you knew. It's when the solid becomes a gas. That's called sublimation. Before you write that down, does anybody know an example of when a solid becomes a gas?
Dry ice.
Dry ice. What is dry ice? CO2, yeah. Frozen CO2. When it melts, it skips the liquid state and becomes a gas immediately. There are other ones too, aren't there?
If you heat something at a really high temperature.
Yeah, at high pressure perhaps, is it? I know there's a way to do it if you put your food in a container. You set the pressure kind of high, I think. You boil the food. It goes straight to being a gas, skips being a liquid. This is how they make the food a powder, I think. You know the instant meals where it's a powder?
Freeze dries.
Freeze dried, yeah. They skip it being a liquid state, so this is why the powder is so dry, because it was never a liquid. But I'm not sure how they do this. But you're right, it's called freeze drying, isn't it?
So they bring the solid to
Yeah, but what do they do with the pressure? Is it a high pressure or a low pressure? You want to lower the boiling point. So that's a higher pressure or a lower pressure? Higher pressure, isn't it? Yes, it's a higher pressure, isn't it? I think. Anyways, no matter. Can you write down the first two sentences? Continue? I just need the first two sentences, Diego, yeah?
Yeah.
Okay, continue.
Continue.
In a liquid, the molecules are attracted to other molecules strong enough to keep the molecules in contact, but not strong enough to fix the structure. So when you have a liquid, the molecule bonds, they are attracted to each other. But unlike a solid, they're not fixed. So they're strong enough to come together, but not strong enough to fix it, so they can still move. Yeah. the molecules continually move. So this means, well, you know the rest of the story. This means the liquid, it takes the shape of the container it's in. If you push the liquid, what happens to its shape? It changes, yeah, or well, and then when you let go, it goes back. And liquids density, usually more or less dense than solids?
Yes.
Usually less dense than solids. Usually, not always. Okay, I think it's enough to write this definition down for liquid. Yeah? Okay. Continue. So the last one is a gas. Now, we've seen the two other definitions, so let's make a go at the gas definition. What could we say about a gas?
The attraction between molecules are weak.
Yes, very weak.
Very weak.
Yeah. And what else could we say? So do you notice in the previous two definitions I referenced the movement as well. So far Dorian has, in a gas, the attraction between the molecules is very weak. What else could we say? What else could we say?
Free to move.
Molecules are free to move. What can we say about their shape?
It's not fixed.
It's not fixed. The gas will take the shape of the container it's in. You can deform it. If you push it, then the gas gets moved out of the way. What did I write? The chemical bonds are not strong enough to hold the atoms together, or the atoms or molecules together. And from this, the gas is a collection of independent, unbonded molecules which interact by collision. So the molecules don't pull to each other. They move around independently and freely. And the only interaction is sometimes they collide. Sometimes. And that's it. Okay, there you go. If you can write that down. Okay, you got that? Yeah. Now, I only got one silly question here. Some ice is taken out of a freezer and placed on a table at room temperature in direct sunlight. Describe how the ice changes over time. So this question, I want us to use all the words we can to describe what happens to the ice. Okay. So first we say the ice begins to what? The ice begins to melt because
It dissolves the heat.
it's receiving heat, it's absorbing heat energy. The molecules of the ice were fixed, but as they receive energy, what happens? They separate and begin to move, and then we have a liquid. As they receive more energy, what happens?
Comes water.
They separate completely, it evaporates, it becomes steam. You know, we don't need to write this down. I just want us to practice using the words. So let's just recall all our words. So we have solid to liquid is melting, liquid to gas, evaporation. Liquid to solid, freezing. Gas to liquid, condensation. And solid to gas, sublimation. These are the key words. Are we okay with that? Now I have no idea what the question is I gave you. It's probably some simple little exam question. Shall we have a look at it? Let's see.
There's one question.
Just one question, huh?
To investigate Brownian motion, a smoke cell can be set up.
Brownian motion, good. What's the name of the lesson? States of matter. Okay. thought I put this question in already. Okay. So, to investigate Brownian motion, a smoke cell can be set up. A light source is shone through a sealed box containing smoke particles, which can be seen as bright dots when viewed through the microscope. Describe the observed motion. Give a conclusion about the nature of matter which can be drawn from these observations. So this question, maybe we'll do it together. It's something called Brownian motion. What they do, oh goodness, the heck, give me a nice black, there we go. Okay, so you have a smoke cell. I don't know what way to draw this. So you have you'd have some light source inside, and then you'd have some microscope here, which you can. There's my eye. Look, I'll make it green so it can be me. There. Right. So you're looking inside. So what you have here, the light is shining on some smoke in the box, and this lets you. If you look in the microscope, you can see the little smoke particles because they're little. So I'll just draw them here as red dots. And when you look at one of them, you'll see it moves around like this. It's not heading in a straight line. It's kind of just dancing around in one spot. This motion is called Brownian motion. Now, what does the question ask you to describe?
Describe observed motion.
So the simplest way to describe that is the smoke particle, or should I say, did I say particle or molecule in the question, or they?
Smoke particles.
They do say particle. Okay. Is undergoing a. Now, does anybody, I'd be very happy if anyone knew this, does anybody know in English the way to describe this motion where you're not heading in a straight line, where you're just kind of dancing in one spot, kind of not moving anywhere? Anyone know it? It has a formal name and an informal name.
Just idling.
Like idling, good. Not this though, but that's good. So, what do you think? So informally, zigzagging. Well, zigzagging's not too bad, and idling's not too bad. Informally, it's a drunken walk. Like it's drunk. It's not moving in one direction. But the formal name for it is, you said a small particle is undergoing a random walk. A random walk. Yeah. Now, what's part B? What can we infer from this? Is it? Yeah. So, does anybody know why the smoke particle might be undergoing a random walk? What is the cause of this?
Bounces against other particles.
That's it, yeah. The reason for this is because it is colliding. Because remember in our definition, we said for the gas, it's a the only interaction is a collision. Remember we said that? So what we could say is, as a gas, the only interaction is a collision. Therefore, the particle of smoke is colliding randomly with what? What did you say, Diego?
With the little particles.
Yeah, but we can't see these particles. We can't see these molecules.
And these molecules.
So what is the smoke colliding with? It's not other smoke, because we could see that, because the smoke is lit up.
The air.
The air, yeah. It must be colliding with the air molecules, perhaps, which is what? Nitrogen and oxygen and so on. But we can't see these. So we can say it's colliding randomly with unseen, smaller molecules, i.e., what's it? O2, isn't it? N2, maybe CO2, etc. Now, why is this experiment important? The reason is it gives evidence for the existence of atoms. Are we happy with this? Makes sense? Brownian motion? Because atoms were only proven to exist, what, 120 years ago, something like this. Before that, people assumed they exist, but there wasn't really any experiment for it. Who did this experiment? You would think it was Mr. Brown. It was actually Einstein who did this experiment. But Brown also did it after Einstein, but they named it after Brown because they didn't want too many things named after Einstein. So Brown gets all the credit, even though Einstein did this experiment first. Also, you've done Avogadro's constant in chemistry. The first calculation of Avogadro's constant was not done by Avogadro, but was done by Einstein as well. So for the same reason, because otherwise you'd have Einstein's experiment, Einstein's constant number 2, number 3, So
Newton was important enough to get the laws holding.
yes, correct, yes. But interestingly, Newton's rivals at the time, he had rivals at the time who discovered the same things he did. And I think the only reason we refer to them as Newton's laws and not say like Leibniz laws or other people's laws is because just, England was an empire and they could do and say whatever they want, So like, why would they name something after a German mathematician? It's like, no, Newton this, Newton that, Newton's 3 laws, Newton's first law, Newton's second law, Newton's third law, forces measured in newtons, I think this is more to do with England's position at the time of Newton than anything else. Okay, so that's that lesson finished and no questions due for homework since we just did it. Did you all write that down?
Yes.
Yep, okay. Let's look at the next one.